Al Gore warned us about adverse climate change. He had a PowerPoint and everything. Now even South Park admits that man-bear pig is real. It's time to get ready for commerce in the Arctic. I'm Super Serial. Here at Midstream Technology in Williamsburg with Elizabeth Simons. Elizabeth is a PhD student in applied science at William & Mary and also lead scientist at Midstream Technology across town. And we've been working together with Midstream and AECOM and Avigia Systems, funded by Bessie from the Department of the Interior, to develop technologies to track oil spills in the Arctic. And we've got a couple of devices that we've been to the North Pole and back with to do proof of concept experiments. And the basic idea is that if oil is spilled in the Arctic, it can get trapped under ice floes. The ice floes move and the oil will move along with it. And once you've found the oil trapped under the ice, the hard part is how do you go about telling where that ice flow is and where it's moving to, and how do you get that information back to the people stateside who are trying to coordinate the remediation of the ice flow. Mm-hmm. And our idea, the thing that Elizabeth is developing, is the part of the project that gets the information about the location of the ice, the oil under the ice, to the top side of the ice, and then to a satellite tag that can communicate back to the stakeholders who are coordinating the recovery. All right? Right. I wonder if you could tell us a little bit about this one, which we've called the pill. So what's inside of there? We can't see the inside.
So inside the pill, up at the top, there's a cone that's made out of foam, mostly air, so it reflects the sound generated by the transducer up into the ice at the angle of incidence.
Okay, transducer.
We
probably should explain that.
Probably should start there.
So this one here, my foot's in the way, but this one, we call the kayak because it's sort of shaped like a kayak, but the big circle there that you can see, what's that?
That is a transducer, and so it sends out a tone burst at, this one's at about 2.3 kilohertz, and it sends it out omnidirectionally, and we put this right onto the bottom surface of the ice and send guided waves up through the ice.
Okay, so this is sonar, but instead of sonar projecting into the water, we project sonar from under the ice up through the ice, and in the ice is a sort of a plate, and these lamb waves, they're called, spread out from that source location, and we pick them up on the top side of the ice. So let's talk about that a little bit. So we've got a transducer either in the pill or the kayak that's underneath the ice that's projecting kilohertz, 1 or 2 kilohertz signal up into the ice, and that spreads out in the ice.
Pick it up with a accelerometer similar to what's in your Fitbit. This was one of the ones that we used at both the testing in New Hampshire and in the Arctic and in Minnesota. And so what this does is it picks up the vibrations in the ice, and then we process that out to determine where, or the distance the transducer is from the accelerometer.
So a big part of the work is signal processing, developing the algorithms that identify the signal that we're transmitting. It's a narrow banded signal, so we filter it and look for those frequencies that we're transmitting, and then the time arrival of those signals allow us to say how far away the signal is, and several of the accelerometers allow us to triangulate back to that source location. But that accelerometer, we use that at tests at the Cold Regions Environmental Research Laboratory in New Hampshire.
Sure, I believe.
Yep. And we also then went to Barrow, Alaska, north of Barrow, Alaska, a couple of times, and one of the most interesting parts about those tests was deploying the accelerometers from a helicopter. And so these are built into a device which we call a GridSat tag. And we actually did yeet some of them from a helicopter and to make sure that they would stick in the ice when they landed, and then the accelerometers picked up the vibrations. The devices that we deploy topside, they form a mesh radio network. Each of the devices has GPS in it, so it knows where it is. And they share that information about where they are with each other, and then one in each group has a satellite modem with it. We're using a Iridium satellite modem so that we get full global coverage. And because only one in each group has to have the satellite modem, that makes the whole thing much less expensive. And so Elizabeth went to Alaska last winter, and they went out onto the ice, and they cut holes in the ice and deployed the pill with a robot, and only dropped one ice saw through the hole in the ice. They collected data with the pill deployed by a robot with the topside tags, and then went to Minnesota.
Went to Minnesota this past winter and did it all again.
Because the tests in Alaska, we didn't get as much data as we wanted. A bunch of the equipment was damaged in shipment, so the guys had to fix that. And then they weren't able to stay out on the ice as long as they wanted because the ice opened up earlier than expected, and they had to pack up and come home. So then the next winter, the crew went back out to a nicely frozen lake in Minnesota, and one of the things that they showed there is the signal that's transmitted underneath the ice. They can pick that up with a topside accelerometer a kilometer away on the top side of the ice. They did those tests in Minnesota. More convenient to get to from Williamsburg than is Barrow, Alaska. Yeah. And so this concept, which we've done now both in a controlled environment at a test tank in New Hampshire, a couple of visits to the north of Barrow, Alaska, and also on a frozen lake in Minnesota, we've shown that you can transmit the ultrasound from underneath the ice, pick that up with the topside accelerometers. Those accelerometers you can deploy from a helicopter or a fixed-wing aircraft, or you can go out on the ice and attach them. And those will pick up the signal, triangulate back to the source location, and then as the ice moves, you can keep track of that to come back and recover the oil that's under the ice. Is that about it?
That's about it.
Okay, thank you. I'm Professor Mark Hinders with the Applied Science Department at William & Mary, as.wm.edu. You can find more information about this project on our webpage. You also can check midstream.us for information about their projects.